Okay. So today, I'm Kristin Lee. I'm a graduate student in Graham Coops Lab at UC Davis. And today I'm going to be talking about a method we've been working on to distinguish among modes of convergent adaptation. And I want to start off by thanking Stacy for inviting me. This has been really fun so far. So as Casey mentioned in her introduction, convergence can be a powerful tool to connect genotype to phenotype. So when you see, I guess I should start off by explaining that I'm defining convergence as being multiple independent routes of selection in multiple populations. And when we see this happening, this can be a really useful tool for connecting both the ecological and molecular basis of adaptation, as we get to see this process happening multiple times. So therefore, it's important to distinguish between cases where we actually have convergence and those where we don't have convergence and either just have a single bout of selection or something that looks like it due to chance. Sometimes phylogeny makes it possible to distinguish these cases of convergence. So if we see the similar phenotype arising across disparate taxa, such as this decreased pigmentation across these three diverse vertebrate species that live on light-colored substrates, we can have pretty good evidence to suggest that that selection has happened 3 times independently and didn't happen sometime in their ancestor. And in this case, we also see that selection was at a single genetic locus, so at this gene MC1R. And for the duration of my talk, I'm going to be talking about this sort of convergence, so convergence happening at the molecular level. And to formalize this in another way, we can see that there's convergent adaptation whenever we see non-sister taxa sharing the derived trait, and we have a good idea that there's not incomplete lineage learning or other complications. So if we have these 5 populations related to each other in this way here, and we have populations 2 and 3 are in some novel selective environment indicated by these blue stars, and the ancestral environment is these orange and red circles. If populations 2 and 3 show the signature selection that's not shared with their sister populations, and we have some idea what the ancestral state was, then we have evidence that selection has occurred multiple times independently. And this can also occur within species, and this tends to be the level at which I think about things as population genesis. So we also have examples of decreased pigmentation occurring multiple times in populations within a single species of beach mice in the southeastern United States. But what can we say in cases where this isn't true? So where things are more complicated or our 2 selected populations are sister to one another. In this case, the selection might have occurred multiple times independently, so there might be true convergent adaptation, here indicated by these lines on these branches. Or there might have been just a single instance of selection sometime in their ancestor before the populations split from one another. And even if this event was truly convergent, so we have multiple independent instances of selection, there's multiple ways that this can occur. And distinguishing between these modes gives us a lot of insight into how adaptation is happening and possible constraints in our system. So the first way that this can occur is that there could be independent mutations once our populations are isolated from one another. So here indicated with these blue triangles, what we see is that there's mutations at the same genetic locus that's occurring once our populations have split. Additionally, selection can be on the same mutation. And one way this could happen is that there could be a single origin of our beneficial allele that is spreading throughout our populations via migration. And lastly, we can have selection on something that was shared in the ancestor of our 2 selected populations. So it arose sometime in the past, and then once our populations are isolated from each other, they're in their novel selective environment, and selection occurs. So we can see this pattern, and there might be many different ways in which this can arise. What we want to understand is how we can distinguish these cases of convergence, and how we can distinguish among these modes of convergence. And what I'm going to do is leverage information from neutral sites that are linked to a selected site. So we know that when selection is happening at some locus, that things that are not able to recombine off that background are also going to hitchhike with them. All right. And as some of our speakers were mentioning earlier, we need to understand the covariance that we're actually interested in, apart from the covariance that's due to shared evolutionary history. So before I start talking about modeling selection in this framework, I need to talk about how we model neutral middle frequencies just due to underlying population structure. So again, we have these 4 populations, and now we're looking at a single neutral locus. And at present day, we have allele frequencies x1 through x4 that are derived from some ancestral middle frequency epsilon. And we can define a matrix of coancestry coefficients that describe this underlying neutral population structure, where on the diagonal we have the coancestry coefficients within populations, that are proportional to the branch length of our population since they split from the ancestral population. We can also think about these as probabilities that pairs of lineages coalesce before they reach the ancestral population. So here we can think of F11 as we're sampling two pairs of lineages, both from population 1, what's the probability they coalesce before they reach their ancestral population, where their allele frequency is epsilon. We can also do this for coancestry coefficients between populations. Here thinking about F12, again, proportional to the branch length that now populations 1 and 2 share before they reach their ancestor. And think about this as probably a pair of lineages, one from population 2, one from population 1 coalesce before they reach the ancestral population. And incorporating selection into this framework, so again, where we have our star populations in some novel selective environment, what we know is that if we have a selected site, at some distance L away, our neutral locus might be affected by the dynamics at the selected site. And therefore, we can define new coancestry matrices that are functions of this distance L away. And to briefly walk you through how these three things look, I'm going to start by talking about our independent mutation model. And what we see now is when we have sweeps that are due to independent mutations in our two selected populations, we have an increased coancestry within our selected populations. And this is controlled by the fact that there's an additional probability that a pair of lineages will coalesce due to the sweep phase. And this is a decreasing function of recombination distance away from our selected site. So what we see when I'm plotting here along the x-axis is the recombination distance away from our selected site, with the leftmost spot being immediately next to the selected site. This is the coancestry coefficient on the y-axis. And as you're immediately adjacent to the selected site, your two neutral lineages are being forced to coalesce due to the sweep phase. But as you're moving further away, you have a higher probability of recombining off that beneficial background, and you're returning to your neutral coancestry. In this model, we see that there's no increased coancestry between our selected populations, and this is just due to the fact that our mutations are independent. Sampling a lineage from both of our selected populations is not going to coalesce more rapidly than any other neutral locus. We see the same effect of this increased coancestry within our selected populations for our other two models of migration and selection on shared ancestral variation. But in this case, we also see that there's an increased coancestry between our selected populations. So we see, and this is due to the fact that selection is acting on the same variant, and something that's either shared via migration or something that's shared via selection on the same shared standing trait. And plotting this in the same way as before, so what we see now is that there's coancestry between our selected populations that's decaying back down to our neutral expectation with recombination distance away from our selected site. And the rate of these decays depends on our mode of convergence and also some other parameters involved. So for instance, in our standing ancestral variation case, if this allele has been standing for a long time, this decay will happen very rapidly, because if you imagine moving backwards in time, it's going to be a lower probability of coalescing as they've been standing independently in our two populations. But if it's short, that decaying coancestry is going to be more on the scale of something that's migrating quickly between our populations. All right, so we put this, what I've showed you is that we can define coancestry matrices that are a function of a given recombination distance away from the selected site for these models of convergence. And what we're going to do is model these neutral allele frequencies as multivariate normal around this ancestral mean epsilon with variance covariance proportional to these coancestry matrices. And with that, we can get the probability that of a given neutral locus and distance L away from our selected site of these observed allele frequencies. And we can do this for all of our neutral loci in a region of interest, and simply take the product of these terms to get a composite likelihood of all of our neutral data in a region. So what this does is this tells us two things. First, we can identify loci that are involved in convergent adaptation. And this can be particularly interesting for trying to find where these genes that are underlying these adaptations are. And we can do this, so if we have a given region of interest, we still will have the same neutral sites sampled, but we can move our proposed position of the selected site and recalculate our likelihoods with those distances. And we can also distinguish between these modes of convergence as these are controlling for the variance covariance between our populations. Okay, so we have done just that in studying the evolution of gluten tolerance in lenticular fish fundulus heterocolitis, and this work has been done in collaboration with Noah Reed and Andrew Whitehead. All right, so what they have done is they sampled, they population genomic samples from 4 pairs of populations across the east coast of the United States, where they have both sensitive and tolerant fish. The tolerant fish are able to live in very high concentrations of pollutants. And what we've done is applied our method to a region that we already think might be interesting, so there might already be this convergent adaptation happening. Because we see that there's an increased FST, which is a measure of genetic differentiation, between all pairs of sensitive and tolerant killifish populations that are sampled. And what we've done is we've calculated the likelihood of our neutral allele frequency data in this region given 5 distinct modes of convergent adaptation. So the modes that we tested are as follows. So the first that we tested is that all tolerant populations have independent mutations at the same locus. So that means that there's 4 mutations at the same locus once their populations have been isolated from each other. The second mode that we tested is that all tolerant populations share something via migration. So there's a single origin of our beneficial allele and it's migrating into our other tolerant populations. The next model that we tested is that all populations share something via standing migration. So something arose in the ancestor of all 4 of our tolerant populations and was selected for once their populations were isolated from each other. But because of what we know about how our populations are related to each other, and that the southern pair here forms a distinct clade relative to our 3 northern pairs, we also tested 2 additional hypotheses. First is that there was an independent mutation in our southern population, and another mutation at the same locus, but now all our northern populations are sharing this mutation via migration or via something that was standing in their ancestor. Okay, so what I'm showing you here are the results. So what I'm plotting along this x-axis is going to be moving our proposed selected site along this region, and I'm showing you the composite log likelihood of our model, and I'm taking out any of the neutral population structure effect. And this is just done by calculating variance covariance matrices on randomly sampled alleles in our genome. And so for any given point here, what we're going to see is 5 different points corresponding to these 5 different models, where the open squares and triangles correspond to where something different is happening in the south, so they have an independent mutation in the south. And what we see is this. So there's 2 things to notice. First is that all of our likelihoods for all 5 of our models of convergence are peaking at about the same place, which also corresponds to where our FSTs were peaking. So this is an indication that under here there might be underlying some trait that was selected for. And what you can also see is that our model where there was 2 independent mutations at the same locus, one in the north and one in the south, but the northern populations were, it was acting as something that was standing in their ancestor, so one here and one here is our most likely model. And because of how these models are parameterized, we can also get back some things that are biologically interesting. So what I'm showing you here is just the profile log likelihood surface for the minimum age of the standing variant. So this is how long our variant has been standing in our populations once they've been isolated from each other, but prior to the onset of selection. And what you see is that this is peaking at about 7 generations, so we have evidence to suggest that this has been around for a very short time before our populations underwent selection. And additionally, we can get back some estimates for the strength of selection and the frequency of the standing variant, so the frequency before it's which was standing before selection started. And what I'm showing you, these yellower colors are a higher composite likelihood, and the red are a lower composite likelihood. And it seems to be peaking at a very strong selection coefficient of about 30%, and it was standing at about 10 to the negative 7. And this is to remind me to tell you that everything that I've talked about thus far, so the models are inference method, and these applications are now up at a preprint that you can check out. Okay, so, sorry. So, these models are parameter rich, which is nice for the things that I've talked about previously, but it also means that identifying the loci that are involved in convergence genome-wide is quite computationally intensive. So what we've done now is capture the essence of these models using just 2 parameters, and those are the correlates of times within and between the populations. And I'm going to briefly walk through the intuition of what's happening here. So going back to our independent mutation model, we see that this additional co-ancestry within our selected populations is governed by this function that's controlling for these probabilities that the pairs of lineages are going to coalesce more rapidly due to this sweep. But we can substitute this with another function that only takes in one parameter, which is the coalescence time within our population. And in this case, this isn't really simplifying anything much, but as you'll see in a moment, this is going to simplify things greatly in our other two modes of convergence. And additionally, we can do this for our increased coancestry between our population pairs, where it's just controlled by a single parameter, our coalescence time between populations. And in our independent mutation model case, this between coalescence time is effectively infinite, as our two mutations are independent, and at the location of the selected site, there's no probability of them ever coalescing, unless you move off that beneficial background. Okay, so what I'm showing you is we've simulated under this convergence scenario, and I've plotted the selected site down right in the middle of this region, and you can see that we are getting a peak in our composite likelihood around the selected site. So what I'm doing is I'm calculating the composite likelihood in windows, where these dots are corresponding to a new proposed selected site. And what you see is this is the likelihood surface of our coalescence time between our populations is peaking at a very large number, suggesting that this is the model that's happening for the independent mutations model. We can very busily do the same thing for our other two modes, where there's been either migration or selection on the same standard variation, and this will really simplify things if we just have a single parameter t within and t between. And what you see in this migration case is, again, we can correctly identify the locus where selection is happening, and now our coalescence time between our populations is some finite value. And this looks the same for our standing variant model. So this isn't particularly insightful for distinguishing among modes, but it is very useful for scanning and trying to find regions of the genome where convergent adaptation have occurred. So we have applied this with Jessica Selby and John Willis, who have 4 populations of Arabidopsis lyrata across, this is Pennsylvania. And what they have are 2 populations that have adapted to live in serpentine soils, which pose a strong selective pressure to plants, and 2 that have not. And what I'm going to show you is the results of this scan, where we're looking for, where we're just simply plotting the composite log likelihood of our model, again controlling for this population structure that exists in these 4 populations across the 8 chromosomes of lyrata. And what you see is that the majority of the points, so this is, again, calculating the composite likelihood for each of these points of the proposed selected site. And now we're doing it in windows of fixed SNP count, so that these composite likelihoods can be more or less comparable to each other. And the majority of our proposed selected sites have a composite likelihood of 0 relative to our neutral population structure, but there's a few signals of selection, or as John Willis would write, with a few more exclamation points, with these signals of selection. And yeah, so what I'm going to do is zoom in on these 2 highest peaks, so here in chromosome 2 and chromosome 6. And on chromosome 2, what we see is this really large peak at the end of the region, and this peak right here has no known function at the moment. So all these have been pretty preliminary results with this. We don't really know what's underlying this gene, so potentially we might have picked up some novel signal of serpentine adaptation. And when we look at the profile log likelihood surface of our coalescence time between our populations, we again see that this is peaking at some finite value, suggesting that this is either due to migration or something that was there in their ancestor. But we can use the previous method to further dissect what's going on here. On chromosome 6, we see a slightly different story, so where this largest peak is happening. This is corresponding to a candidate polymorphism that Tom Turner and colleagues had found previously in similar populations of Arabidopsis lyrata. And this corresponds to a gene that's been annotated in Arabidopsis thaliana for a magnesium transporter. And this makes sense with our serpentine soils, as they have low calcium to magnesium ratios. And again, we see some finite values in between, suggesting either that these 2 serpentine soils are sharing this either by migration or selection of something that's genuine in their ancestor. So to conclude, What I've walked through is a statistical framework that can help identify these loci that are potential targets of convergent adaptation. And in particular, this approach might be more powerful than other typically used approaches, such as doing pairwise FST comparisons, because we can do, this is incorporating information across a large number of populations, so all of our populations sampled. Additionally, you don't need to sample population pairs where one is under selection and the other is not. You can use everything that you have and put this into this framework. And you don't necessarily, a pair, need to know anything about their relationships to each other. Our model is taking into account that population structure. And from there, we have showed that we can distinguish amongst these distinct modes of convergent adaptation. And you can do this in many different scenarios. You can imagine, as is exemplified in this complex case with the killifish, where you have one population doing something differently from the other populations, or any sort of larger combinatoric thing related to this. All right, so with that, I'd like to thank the Coop Lab and you all for listening. Thank you. I have a lot of time for questions.
So are you modeling gene conversion in your recombination model, or just increase resistance intercrossing?
Not gene conversion, no.
So how will that affect this?
That I have not thought about, but happy to talk about it. Yeah.
Can you explain what's going on with the ratio test there? I didn't quite follow with the subtracting off the neutral.
Yeah. So maybe just going here.
Yeah.
Okay, so we're getting a co-ancestry matrix from our neutral sites in the genome. So in this case, what we're doing is randomly sampling a bunch of SNPs across around the genome. And we're calculating variance-covariance matrix of those alleles. And then when we're looking at a single proposed selected site, we're taking everything around it, some fixed window size, and recalculating the likelihood under different models. So in this case, what we're doing is just taking the ratio of calculating under our model where we have only 2 parameters, the within and between times, and then taking out the population structure. That would be if we just ran our composite likelihood of everything in this window using our neutral co-ancestry matrix. Yeah.
Have you tested the sensitivity of this method to window size?
In this case, no. And actually, so this is not actually based on window size, it's based on how many SNPs are in a window. So we know that there is some confounding of how many SNPs you have in a window and composite likelihood, since it's taking each of those observations as independent. So we try to control for that by looking at fixed SNP window instead of size. I think it will be sensitive. Yeah.
I guess I'm wondering, a lot of these examples were at a pretty recent scale. What do you think the challenges would be with going deeper? I mean, I thought it was really cool being able to dig these alleles and things, and we have our whole genus.
Yeah. So continuing your advanced takes questions about going on deeper timescales. I think as long as the signature of selection is still there, so it wasn't selection that has been soup is old and therefore that signal is degenerating over time, I think there might be still power to detect these new things, but we're really excited to try. That was a question.
Are you guys going to try anything like that?
There's no plans at the moment, but yeah. Other questions? Ask the church. Okay, thank you.